Guillaume, can you hear us okay? Can you just speak out so we can see if we can hear you?
Yeah, I can hear you. Can you hear me?
Okay, great. So you've got 4 minutes and starting from now.
All right. Yeah, thanks. So I'm Guillaume Guiglion, postdoc at the Leibniz Institute for Astrophysics, Potsdam. And the idea of the work I'm going to talk briefly is about parameterizing stellar spectra in the context of the large spectroscopic surveys such as APOGEE, RAVE, Gaia RVS, and the incoming surveys such as RAVE and Foremost. So why do we want to derive spectroscopic parameters from spectra and chemical abundances? Well, to perform galactic archaeology, because chemistry is important for example, disentangling the stellar populations. So spectra are the unique way to derive chemistry. And actually, you can derive chemistry from intermediate resolution spectra, such as the RAVE spectra from the RAVE project I show on the top left of the poster. Those are intermediate resolution spectra centered on the calcium triplet, infrared calcium triplet, and those spectra are very similar to the future spectra from Gaia RVS we're going to get next April. And the idea to parameterize these 400,000 RAVE spectra, we want to use machine learning. So this is a paper we published in 2020. And we want to use convolutional neural network approach. And there are several reasons why. Well, because we want to deal efficiently with the noise in the spectra. And also neural networks are very flexible. So you can combine stellar spectra, stellar parallaxes, basically from Gaia, and photometry, for example, from 2MASS, WISE, and Gaia photometry. And a unique way to do that is to use convolutional neural networks. So that's a very powerful tool. And the training set was composed of 4,000 stars, and we took the stellar labels, so atmospheric parameters and chemistry, from the APOGEE DR16 catalog. And also for each star, we require that we have parallaxes and photometry. Then, thanks to that, actually, we managed to extend this scientific output from the RAVE survey, deriving abundances for hundreds of thousands of stars, covering a large wavelength range, a large galactic volume in terms of galactocentric radii and Z above the plane. But the main achievement was actually, if you have a look at the right side of the poster, this is the kill diagram we get for RAVE stars with signal-to-noise ratio between 10 to 30. And we're going to have a lot of spectra like this for Gaia RVS. That's why we want to parameterize this. While this is what we get with a standard spectroscopic pipeline, where actually the RAVE spectra suffer from spectral degeneracies because of the lack of information. So you can't disentangle well between the cool dwarfs and the cool giants. But we managed to do that with the convolutional neural network coupling spectra, parallax, and photometry. So that's a great improvement and a good insight for the future Gaia mission. And this is, for example, another machine learning approach, the Canon from KC 2017. And still, with this type of machine learning using just spectra, you can't well parameterize the red clump, while with convolutional neural networks, photometry, and parallax, we do a very, very good job. And this is well seen in the right plot, where we compare with seismic gravities, for which seismology can provide very precise and accurate log Gs. So the dispersion here with our neural network is about 0.14 dex, while for the rest it's both around 0.45 and 0.30 dex, so not so precise and accurate. Well, we have seen with this poster that convolutional neural networks are very powerful for stellar parameterization, and we are looking forward for the next Gaia release that will provide millions of low signal-to-noise ratio spectra, similar to RAVE, for which we'll be able to derive chemistry and atmospheric parameters. And with that, we will study in more detail the formation and evolution of the Milky Way. Thank you.
Okay, thanks very much. Great for staying on time.